I'm excited that we're getting into triangle congruence because this is really the first part of geometry where we can start to use our knowledge about triangles and our knowledge about proof and combine it all into one big party. So we're going to start today by talking about triangle congruence methods. And these are methods of proving that triangles are congruent. And just to remind you, congruent is the fancy geometry word that we use to say two things are equivalent to each other. So we don't really use the word equal anymore. In algebra we would use the word equal, like x is equal to 3, which means that x and 3 are the same thing. But we don't really say the word equal in geometry because we're not just dealing with values anymore. We're not just dealing with numbers. We're dealing with whole figures. You know, they have sides and lengths and angles and orientations and all kinds of stuff. So getting at this idea of equality is a little bit more nuanced in geometry, and so we use the word congruent kind of in the same way that we would use the word equal in algebra. So we're saying that these two things are congruent if they meet certain criteria that effectively make two triangles equivalent to one another. And so we have different ways of doing this. We can say if all three sides are congruent, we say that we have side, side, side congruence. If we have two sides and the angle in between them, then we have side, angle, side. If we have two angles and the side in between them, we have angle, side, angle. And I want to just also mention here that Virginia, for whatever reason, Virginia teaches another method that I don't really agree with. They teach, and on the SOL they teach AAS, which of course is angle, angle, side, and they actually teach this as a separate method than this, but it's a cousin. This is really a cousin. This is really the same thing as ASA. These are really the same thing. Why? Well, because if you know two angles of a triangle, then you know the third one, right? So this is just saying you're kind of, instead of having angle, side, angle, it's like saying that you put another angle out here and then you're dealing with that. But you already know the third angle because you already know two. And if you know two angles in a triangle, then you also know the third one, right? Because you can subtract it from 180. So here's an example of this. Suppose you are given this triangle with angle B, side A, and angle C. So here's angle B, side A, and angle C. Well, think about it. You also know angle A up here. You know the third angle because if you know two of them, you can just subtract them from 180. All three of the angles sum up to 180. So if you know these two and you know that they equal 180, then you just have one unknown value and you can use algebra to easily solve for that value. So that is why I don't really like this AAS thing, because it's really the same thing as ASA. It's just taking it one step further and going, okay, well, we've solved for the third angle, and now we're going to call it AAS, and we're going to call it something different. So I don't really like that, but Virginia teaches it, and so hear me now, I'm saying that ASA and AAS are the same thing. Okay. Now, of course, you're probably looking at these letters and going, oh, SAS, ASA, AAS, I can spell a bad word. I can spell the word ass. I could spell the word ASS with these letters, but I want you to remember that ass is bad. Ass does not work. ASS does not work. And so we're going to learn about this in just a second and why this doesn't work. And we're going to come back to what happens with right triangles, which is really cool. So before we go any further here, we're going to look at what does and doesn't work. And I've alluded to some of this, but we're going to go over to my friends at GeoGebra right here. And I have a GeoGebra book pulled up. And we're going to look at some of these things that work and some of these things that don't. Okay? So here we have side, side, side. And what this is saying is that we have an existing triangle, and we have all three sides are given to us, and then we've copied these three sides here. So here's the 6, here's the 5.3, and here's the 4. Okay, so here's 6, 5.3, and 4. So if I just have this triangle that's given to me, and I have these three segments, the only triangle I can build is going to be equivalent to this triangle, because there's no other way for me to arrange these sides as they're given to me and come up with a different triangle than this. So let's leave the 6 on the bottom, okay? And then let's take the 5.3, and of course if I put it up here, if I connect the 5.3 at this end, like it's done in the original triangle, you can start to see that I'm going to start approximating the same triangle as before. And if I just put this 4 and connect it at this end, then I'm going to start to see that I'm getting the same exact triangle as before. Do you see how those are the same triangle? They're equivalent. You might say, oh, well, maybe what if we arrange it a different way? So let's just do that. Let's put the 4 and connect the 4 on the right hand side over here. Okay, let's connect the 4 over here, which is different, and let's connect the 5.3 over here. And as you can see, there's only one triangle here, and it's essentially a mirror image of each other. They're mirror images of each other, but in geometry that doesn't matter because they're still congruent. Notice that they still have the same side lengths in the same configuration, and they're going to have the same angles because the sides have the same relationship to each other, so the angles are going to be the same. And so with a triangle, of course, you have 6 parts, you have 3 angles and 3 sides, and here we have 2 triangles, and you know, correct me if I'm wrong, but I'm not wrong. These 2 triangles, as you can see, have all 3 sides are congruent to all 3 of the sides in the other triangle, and the angles are also. So we have 2 triangles here that have the same angles and the same sides, and so they are congruent to each other even though they look like mirror images. Okay, they're geometrically congruent. All right, let's look at another SAS. Okay, so here we have remember SAS was side, angle, side. It's 2 sides with an angle in between it. And when I say side, angle, side, I'm talking about just picking a place and I'm going side, angle, side. They're touching each other, right? They're consecutive, and that's why we call it side, angle, side. So here I have the I have the pink side and the pink side. They're both 7. I have the blue side and the blue side. They're both 10. And I have the angle in between, which is 85. Alpha is 85, and over here angle beta is 85. So what happens if I start moving these points around? Okay, notice that, notice that if I move the angles here, if I change any of these things so that I still have side, angle, side congruent, notice that in both triangles I have side, angle, side, right? Side, angle, side. And notice that no matter how much I change this, the 2 triangles are the same, which means that I cannot have side, angle, side in a triangle when I'm saying they're the same. So I have 6.5, 6.5, 105, 105, 5.5, 5.5, and I can change this. I mean, do whatever here. Let's make this 4. Here I have 4, 4, 6, 6, and the angle in between is 105, 105. You want a smaller angle? Let's change it to a smaller angle. I have 4, 4, 50, 50, 6, 6. I still have side, angle, side, and notice that no matter how I arrange this, the triangles are still congruent to each other. Okay, so side, angle, side works. Oh, I didn't want to do that, sorry. Okay, now here is SSA, or if you flip it around, ASS. this is a bad one. This does not actually work because look what I have here. If I have angle A set at 30 degrees, right? 30 degrees. And then I have a side 9 and a side 3. It does not matter. I could actually, put in this side right here to connect the little swinging side to point A. And if I put that in, I can make lots of different triangles here because I can make two different triangles because this angle, the swinging angle, is not fixed. So look what happens when I extend side A, and notice there, okay, there it's starting to touch the line, because of course if angle A is locked in, if I lock this in somewhere, right? If I lock this in, okay, notice what's happening. Notice what's happening. The longer that I make this side, it starts to touch, but I get two possible triangles out of it. And notice that I'm going to make this really obvious here. So notice that I still have angle A set and side B set and side A right here set. I still have in this configuration, I have the angle set at 32, I have this side length at 9, and I have this side length at 5.7. But the fact that this angle up here at C is not locked in means that I can swing this thing back and forth and I can make two different triangles out of it. I get this one here, and I get this one when it swings over this way, and I get this one again, and both triangles are technically meet the ASS requirements, but they're clearly not the same size, right? The smaller triangle and the larger triangle here, and I'm talking about this entire larger thing, not just the lighter shaded part, but the entire larger thing. They're clearly not the same triangle, right? And for the same reason, angle, angle, angle doesn't work because notice here, okay, I'm going to leave all three of these angles the same. All right, I have all three angles the same. And notice what happens if I increase the size of the triangle, all of the sides are changing. But notice that all of the angles are staying the same, 100, 55, 25. And I can bring it really, really small, and I still have, let me see if I can see it there, I still have 100 and 55 and 25, and I can make it larger, and it's still 155, 25, and I can even make it bigger, and all this other stuff. I still have 155, 25. So the angle requirements are all set, angle, angle, angle. But clearly, these triangles, that huge triangle that's even going off the screen, is not congruent to this little tiny triangle right there. They all have the same angles, of course, but that does not mean that they're congruent. So angle, angle, angle is not sufficient for showing congruence. I want to show you a couple of proofs here. This is kind of a foreshadowing for what we're going to be doing in the next video. Let's look at side, side, side. So if I have side, 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 okay, I copy one side, and I don't have to put them in the same position, right? So these two triangles are in totally different orientations. This one is kind of tilted one direction, this one's kind of tilted the other, but the orientations don't have to be the same because we're not looking at what pictures look like or what the shape is drawn like. We're talking about actual geometric figures, and do they meet the requirements of being the same as one another. So look at this side. Side C, I'm taking it and I'm putting it over here. Then I'm taking side A and I'm putting it down there, and I finally take side B and I put it over here. And notice that the area of the triangle is the same. Okay, notice that. The triangles look very, very different, but if I copy the area of one and I look at what is it the same, oh my gosh, it's going right in there. Okay, here's an SAS, here's a SAS proof. So again, we have side, angle, side. So we have side and then the angle and another side, right? So I'm copying this side, I'm copying the angle on the other side, okay? And now notice what happens to the area. There it is, okay? Side, 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 Okay. Side, side, side. We already did this one. I'm just going to show it to you again. Boom. Okay. What about ASA? Okay, here I have angle and the side in between and then the other angle. Okay, so here I have angle, side, and an angle. Now notice before I go any further, I still have angle, side, angle. Or if you want to start with the blue, or maybe it's purple. If you want to start with the purple one, I have angle, side, and then the pink angle. But notice that my area, my triangle is still actually congruent. Even though they're not in the same configuration, I still have congruence there. Okay. Now let's quickly look at SSA, which is AAS, or excuse me, ASS, AS. This does not work. Okay. So let me show you what happens here. Okay. So there's an angle, side, side. We already looked at this. Okay. And so in that case it works. In that case it works, but look what happens. And notice that you can draw this to work, but look what actually can happen, which is why this doesn't work from a theorem point of view. Okay, so here I have ASS, ASS, right? And notice what I can do. I've got my A, I've got my S, and I can swing out this side, just like in the little dangling applet that we just showed you. This other side can be swung out further to where it crosses a second time. Let's just go back to this right here, called the ambiguous case. You see what I'm saying? You can swing it out. You can take this would be the smaller, and I can swing it out to the bigger one, and I get two different triangles. That's why ASS doesn't work. Okay, so we're now going to look at something for right triangles. This is interesting. Right triangles come with a lot of extra material and information for free. Okay, right triangles have hypotenuses and legs, and of course a hypotenuse is the side across from the right angle. It's the longest of the sides, and the other two are called legs. And you get one piece of information for free with right triangles. You already know that one of the angles is 90 degrees. Okay, and another thing with right triangles, you have the Pythagorean theorem. So if you know two sides, then you automatically know the third side. And that's unique to right triangles. So you can start to deduce what I like to call a shortcut for congruency. And that shortcut is HL, hypotenuse, leg. So if you know the hypotenuse and the leg, that is sufficient. Okay, that is sufficient for proving congruency with right triangles. Okay, so if we have a right triangle here and we have hypotenuse and leg, then we already know two of the sides, so we can find the third side excuse me, by the Pythagorean theorem. So this would be given, right? This right angle is given. It's a right triangle. So technically we have ASS. If we're going this way, we have ASS, right? We have ASS. ASS, right? So technically this is ASS, which doesn't work. But with right triangles, you can employ the Pythagorean theorem to get the third side, and then if you know the third side, then you have SSS, which we showed works, because then we have side, side, side. We have all three sides, which is good to go. Okay, so let's look at a couple of examples. I know this is going to be a longer video, but I can't really help that because this is a lot of new material here. Okay, so I'm just going to pull out excuse me, pull out a couple of examples here to look over. Okay, let's look at this one right here. Alright, I'm actually going to zoom in on this. Boink. Okay. Alright, so look what we've got. In these two triangles, we know they're congruent because we have A, we know this angle is congruent to this angle, right? They both have the same congruent marks. We also know that this angle is congruent to this angle because of the congruent marks. And notice what we have in the middle, and please don't overlook this part. This side is equal to itself. And remember, sides are anything is equal to itself. I guess any length, any pure number, anything is equal to itself because of the reflexive property from algebra. Remember, A equals A. So any side here is equal to itself. So whatever that side is, if this side was, DE, then we could say that DE is equal to DE. The length of DE is equal to DE. Okay, or the line segment is congruent to the line segment. Same thing here. Notice here we've got this side and this side. Of course, we've got, oops, I'm sorry. This side and this side. We've got this side and this side. And then notice what we have. We have this third side is congruent to itself. And so that side is equal to itself. And so we indeed have S, S, S. Okay? Here we have, notice we have this side is congruent to this side. And again, when I'm saying this, I'm talking about this length right here. Okay? I'm talking about that length and this length in this triangle. Those are congruent. And we know, okay, and we know that this angle is congruent to this angle, right? And then last but not least, what do we have here? Well, we know that this is congruent to that. Why? Because they're vertical. They're vertical angles. And so we indeed have ASA, okay? All right, I'm talking about ASA right there, okay? ASA. So that's how we have angle, side, angle on that one. All right. Here, these are right triangles, but don't be fooled into thinking it's automatically hypotenuse leg, because we have, those are congruent because they're vertical, and so we actually have angle, because all right angles are congruent to each other, right? Angle, side, angle, and it is the same as angle, side, angle. So that would be that one. Let's look at one that's not congruent. Well, here we have angles and we have sides, but that's not sufficient. There's nothing to say that those are congruent because we don't have enough components. We only have AS, and that doesn't do anything for us, right? Let's look at a side angle side right here. So here, and these are, we're going to see a lot of these. Actually, let's see a lot of all of them. But here we have, side, and again, I'm talking about these sides, this side and this side, okay? Side, this side here is congruent to this side here, so side, side, and then what do we have? Smack in the middle, we have vertical angles, so we have side, angle, side. See that? Side, angle, side. Side, angle, side. Okay. I don't want to keep beating this up too much, but let's look at one example of a hypotenuse leg, just so that you can see one. Here's one. I just want you to see a hypotenuse leg example. Ignore all these. Alright, so right here, number 2. Alright, so here's a hypotenuse leg and a hypotenuse and a leg. And of course, we know those two. Then we also know the third side because we could just throw in a little Pythagorean theorem, and then of course we have SSS. Okay? Alright, that is it for this video.